I think you can start it.
Okay, today we're going to solve the question called first bad version. So you're a product manager leading a team. The latest version of your product fails a quality check. Since each version is based on a previous version, all versions after a bad version are also bad. Suppose you have n versions, 1, 2, 3, all the way to n, inclusive, and you want to find out the first bad ones, which cause all the following ones to be bad. You have an API boolean, which turns whether the version is bad or not. So this is going to return true or false. True means bad, false means good. So we only care about the bad ones when it returns true. So whether version is bad, implement a function to find the first bad version. Should minimize the number of calls of the API. Okay, so first thought is binary search. So we know that on a number line, let's say we have 1, 2, 3, 4, n is 5 or n is 4. If 2 is not bad, means 2 is good, then we know that 1 is also good, because if 1 was bad, it would have caused 2 to be bad. So that means we can move the left pointer upwards. So this is binary search, and for example, let's just draw a few more examples. So 1, 2, 3, 4, 5. Let's start left at 1, right is at 5, and we're going to find the midpoint. So mid is 3. We're going to call this API to say is 3 bad. 3 is good. So that means that 2 and 1 also must be good. So that now we can move left to 4 to mid plus 1, because that's how the binary search works. And then we can find the midpoint, which is 4. 4 is bad. So what does that mean? Well, just because something is bad doesn't mean that it's the first bad version, because we want the first bad one. So we have to move right down to mid minus 1 in order to find the first bad version. Unless it crosses left. Because we already knew that 3 is good, and we know that 4 is bad. So that means we already used process of elimination and we found our answer. So 4 is the first bad version, right? So hopefully this makes sense, but it's really about using process of elimination. Just because a version is bad doesn't mean it's the first bad version. We have to find a version, something before could have been causing this version to be bad. But we know if it is a good version, again, that means nothing before it could be bad, because if they were bad, then the current would be bad as well, right? So that's the thought process behind this. So to code this up, we're going to use left and right equals to 0 and n. So you can imagine like a number line again. And left here and right here are the numbers and not the indexes, because usually we're given in some kind of an array and we have to index into it. But this time, these are just the numbers, aka values themselves. And binary search dictates that the pointers must not cross. And then we find the mid one. So we're finding 3, for example, or 2 in this case. And then we call this API. If is bad version mid, if it's true, right? True meaning bad, then something before it, as we talked about, could be causing our current 2 to be bad. So this is not necessarily the first bad version. So that means we move right to mid minus 1. In all the cases, if it's good, then first of all, our current good number isn't the first bad one, and everything before it isn't the first bad one either. So the soonest the first bad version could be is the very next number to the right. So we move left to mid plus 1. And since we want the first bad version, and we're going to move right and left closer to each other until they cross, at the end, the first bad version is going to be left, because that's the way the algorithm works using process of elimination. So let's run this. Okay. So as you can see, it passes all test cases. Again, this is a classic binary search problem, really helpful to understand what the question is asking in this case.
Yeah, I think yes, definitely yes. So what is the time capacity?
Time complexity here is O of log n because binary search is more efficient than traversing the entire array because we're throwing away half of it every single time. So on the order of magnitude, it's going to be log of n, which is better. And space complexity is O of 1 because we're not using stacks or dictionaries or what have you to store the result.
Okay.
So the most efficient memory complexity we're iterating or utilizing here.
Yeah, I think yes, that's true. Yeah, you are really professional. Yeah, I will start recording.